Hey y'all, we are Memphis Communiversity and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. And today we are going to conclude our area and volume unit with the lesson on arc length. So sometimes arc length is asked as the perimeter of a region, but basically what arc length is the total length between two x values on a certain curve. Keep in mind that arc length is only a BC topic. It is not an AB topic. It is not found on that portion of the exam or that version of the exam because arc length is related to parametric equations, which is going to be the last part of the BC curriculum. But even though it's a BC topic only, it's actually the easiest part of area and volume, in my opinion, for that entire unit. Unlike with revolution, volume by revolution, where you need to know washers, you need to know inner radius and outer radius and how to spin it in pi squares and all of that stuff, or with volume by cross section, where you have to be perpendicular to the x or the y axis, you have to have shapes jumping onto the page. You need to know the formulas of semicircles and isosceles right triangles. This one is just one simple formula. You never usually do the formula because it's too difficult to actually take these integrals. So you just usually set it up and maybe type it in a calculator and maybe you just write the integral and you're done. So what we're going to see is that this sort of process is very easy. So we might as well get started. Because we're doing calculus wrong, we're not going to prove the formula. If you want, you can check out a textbook in terms of the proof, the step-by-step proof on what we're trying to do here. But we're just going to practice the formula, state it, and then just go for examples. So this is arc length. Arc length. Again, on the BC topic, but we like it on the BC topic because it's one of the most, maybe the easiest BC multiple choice question when it's presented. So again, what we're trying to do is we're trying to have a function and we are going to try to measure it from some A to some B. So this is A and B. And basically we're just trying to measure how long this is. This curve right here. What happens is that we break this up into various points. We use the mean value theorem, we use limits and sums and things like that. But in the end, we just get this one nice simple formula. It doesn't involve an integral because we're making these pieces individually very, very small, and then we're adding it up, which is an integral. So let's get started. So the main examples of this, of course, is when you have y as a function of x. So what we're going to do is we're going to try to find the arc length formula. The arc length formula, well, you do need an interval, so it's going to say x is between a and b, but you don't have to plug in these numbers. They can be just random numbers, basically. They're just going to be on the integral. What's the formula? The formula is the integral. I don't know why my colon is not working, but it's going to be the integral from this bottom number to this top number, square root, and it's basically the Pythagorean theorem. 1 plus the derivative squared. So there's not much to know about this formula. Again, it's square root. It does involve a derivative. It involves a squaring, and you just set it up. No number in the front. Usually you don't have to do this integral again because it's too complicated, so you just might leave it like this, and you might plug it in a calculator. Sometimes your functions are not going to be in terms of x. Sometimes it's x in terms of y, but it's the same thing. So let's say we have x is equal to some function in terms of y. Then you're going to have an interval of y, and the parametric formula is again the same. It's from C to D, whatever the y interval is, and instead of 1 plus this derivative squared, it's going to be 1 plus this derivative squared. So it's nothing new. So basically y's and x's are switching positions, but it's going to be this derivative, and it's going to be dy. So again, easy setup, just do the integral. And eventually in the future, or perhaps right now, you might be dealing with parametric functions. Parametric functions, if you didn't cover them in pre-calculus, it's just when you have two variables, the x-coordinate and the y-coordinate, and they're both dependent on the same parameter or parametric variable. So in this case, usually we use t's. So what's going to happen is that x is going to be in terms of t, so it's going to be f of t, something like t squared or something. Then y is going to be another function of t, something like sine of t. So g of t, this is a y. So the formula, again, we need an interval, so it's going to be something like a's and t's in between a and b. And it's similar to this formula. It's still the Pythagorean theorem. It will still involve an integral. So it's going to be a to b now, because that's the endpoints of the interval of t. Then it's going to be a square root as well. But instead of having 1 plus the derivative squared, because you have two derivatives, it's going to be derivative squared plus derivative squared. So in this case, it's going to be f of t squared plus g of t squared. One thing I forgot, which is the most important thing, is actually taking the derivatives. So let's put derivatives. So again, it's 1 plus the derivative squared. In this case, we have two derivatives, so it's the derivative squared plus the derivative squared, square rooting for the Pythagorean theorem, integrating to find the length of everything. So these are the formulas. Again, they're pretty easy, so we might as well start with examples. Pause the video, write them down. I'm going to erase them. Let's go for examples. So let's erase. So let's get started. So we can start off with some complicated function because again, all it is derivatives. So we're going to start off with this function y is equal to 3 to the x times x to the 4th. So this is going to be my function. So basically what I'm asking is, there also needs to be an interval, so let's write x is equal to 1 to x is equal to 3. Let's put 7 instead, because I'm feeling a little bit frisky. But again, what we were asking is you just draw this function, look between 1 and 7, and see how long it is. So again, it's a very simple formula. You write an integral sign, you put the endpoints 1 and 7, you put a nice, beautiful square root, and then you write a 1 plus, put some parentheses, and whatever's in this parentheses will be the derivative. So in this case, looks like it's going to be 3 to the x. Keep in mind that when you're taking derivatives, of course, you need the power rule, the product rule, the quotient rule, and the chain rule whenever they arise. In this case, it's going to be the product rule. So it's going to be 3 to the x times the derivative of x to the 4th. That's the power rule. We take the 4, bring it to the front, of course, subtract 1. If you're watching this video, you're probably pretty good at derivatives by now. You might have forgotten the derivative of 3 to the x, a to the x. Keep in mind, you do not use the power rule for this. The derivative of 3 to the x is 3 to the x times ln of 3. We're going to keep the same, of course, so it's going to be times x to the 4th. We're going to close that parentheses, and we're going to remember the square. So it's 1 plus the derivative squared. Then we write a dx. And that's all it is. Again, 1 plus the derivative squared. We did product rule. Keep the same derivative of the first one. Keep the second one the same. But notice how easy this formula is. It really is just a derivative question because these integrals are so complicated. So all you have to do is write a nice square root, 1 plus, and then have the derivative squared. And that's it. There's nothing much to say. Like, this is the answer. It's a one-step question where you're just taking derivatives. So let's see how it's not much different when you have x's in terms of y's. Keep in mind that when x is in terms of y's, y becomes the independent variable, so you don't need to implicitly differentiate what I'm about to write on the board. Let's do x is equal to sine of e to the 4t plus 3 ln of t or something like that. I don't know why I have t's, let's use y's. So again, even if you have y's, we're not going to multiply by y primes because y is actually the independent variable in this case. So basically it's the same as that question, except we have y's now. Let's go from y is equal to 3 to 8. So again, all you do is you write a nice beautiful integral. You write 3 and 8. The bottom number is the smaller number. Just like normal, the top number is the bigger number. Write a nice big square root. Look how big we can write because there's so few steps. We can write everything pretty big. It's going to be 1. I can write a 1 here. Plus, and then whatever is the derivative, squared, and then we'll put dy at the end. So the derivative of 3 ln of y, that's pretty easy. Just going to be 1 over y times 3, of course, because that's the derivative of ln. Then what's the derivative of sine of e to the 4y? Again, the most important thing, of course, is the chain rule. The chain rule is the most important part of my life. I don't know about you guys, but what's the derivative of sine of e to the 4y? It's going to be cosine of e to the 4y. But you do have an inside function of e to the 4y, so we need to multiply by e to the 4y. Because that's the derivative of the inside. But there's a new inside function, which is a 4y. Just a nice little double chain rule action here. But again, you're probably pretty good at derivatives, but this is going to be times 4, and we're good to go. So again, as long as you take the derivative correctly and you don't erase your plus and things like that, you should be good to go. Just keep in mind that the derivative should be squared within this parenthetical element. Form the formula. Just remember the chain rule and the product rule and things like that. Chain, because the derivative of e to the 4y requires another derivative, and the derivative of 4y requires another derivative. Times 4 times e to the 4y times 4. And that's all it is. As long as you can review your derivatives, you should be good to go. So let's try to define one with those parametric ideas. So let's erase this. Let's say we have something like x is going to be, let's see, what do we want? So let's say x is equal to, I don't know, 2t squared plus 3. And then we have y of t, so we can maybe write x of t. Let's say y of t is equal to 3 over t minus 2. And then we're going to try to write the formula where t is between 1 and 6. So again, even if you have these parametric questions where you have two variables in terms of a third variable, in this case we have x and y, both in terms of t's, it's the same thing, just slightly different square root of not just 1 plus derivative squared, but there's two derivatives, so you put derivative squared plus the derivative squared. So in this case, we're going to draw that beautiful integral. We're going to go from 1 to 6, because that's where the parameter goes. It goes from 1 to 6. Then you just set up a nice big square root. You write the derivative squared. This is going to be the power rule, of course. We drop the 2 down. It's going to be 4t squared. Why is the squared here? Well, again, it's the derivative squared. So the derivative of this was just 4t, but we're squaring it. Then we have the derivative of this guy right here. Keep in mind that we shouldn't do the quotient rule, even if it's 3 over t. We're going to do the power rule because we're going to write it as a negative exponent. In my opinion, that is easier. The derivative of minus 2 is 0, so that'll be easy to deal with. Again, what's the derivative of 3 to t to the minus 1? Well, that's going to be just negative 3t to the minus 2. Because we're avoiding the quotient rule, we're doing the power rule instead. Taking the negative 1, allowing the negative 1 and the 3 to meet, it becomes negative 1. Then we subtract 1 from the old exponent, it becomes negative 2. The derivative of minus 2 again is 0. So all we have to do is just squared. And this is it. This is the answer. If you needed to, you would type this in a calculator, but you probably don't need to find this integral yourself. Keep in mind though that if this is a multiple choice question where the answer are these integrals, just be wary of the squaring and just make sure that both of your derivatives are squared. So for example, if we were to simplify this, which potentially the answer choice could be simplified, we would write a nice big square root still. But keep in mind that, for example, for this first derivative, the 4 is also being squared. So you would want to choose the one that says 16t squared. Well, this is the same thing as negative 3 over t squared. When you're squaring a quotient, you're squaring both the numerator and the denominator, of course. So if you're simplifying this side, it would be something like, well, negative 3 squared is 9 over t to the 4th. So just be careful that you're squaring both of these. Again, it's not a hard question, especially if the answer choices are presented as these integrals. Just be wary of a few things. Remember to take derivatives actually. Remember to square them. And if you're squaring them, remember to square the entire derivative and not just the variables. But if you do that and you have your square root, you should have the correct answer. So let's try to form an arbitrary question because again, just these setups aren't too exciting. So let's try to form an arbitrary question where we might actually be able to take the integral. Again, this is a rare occurrence because usually with these random functions, you just leave it like this, but we might as well take one integral just to practice. So I'm going to erase this. And we're going to have the function, we're going to go back to y's and x's because I'm more used to that. And we're going to have the function, let's do 4/3 x to the 3/2 plus 1. And what we're going to do is we're trying to find the arc length of this function, meaning the length of this function from x is equal to 0 to x is equal to 2. So this is going to be my guy. Let's try to go for this and let's actually try to compute this answer because I don't have a calculator with me. All the previous ones you could have typed in a calculator. Just be careful of obviously if you're using a calculator. But let's try to actually do this one because I think this one will be possible based off the formula. So in this case, what you do, of course, is you write your bottom number 0, you write your top number, then you put a square root sign. 1 plus, because there's no t's, it's just the derivative of this guy. What is the derivative? Remember that this is the power, of course, so we take the 3/2, drop it to the front. What's 4/3 times 3/2? Well, if you notice, those 3's cancel quite nicely. 4 over 2, of course, is just 2. So I think we're going to be left with 2. Then the new power, what's 3/2 minus 1/2? So, 3/2 minus 1, so you're going to form 1/2 as the new exponent. We're not going to forget the square because the formula says 1 plus the derivative squared. So we're not going to forget the derivative squared. And then we're going to write dx. Again, this integral is possible. So let's simplify this integral and let's actually go for it. So it's going to be the integral from 0 to 2, the square root of 1 plus, Again, keep in mind that when you have these constants, they need to be squared as well. So this is going to be 4x because x to the 1/2 or the square root of x, that squared is just x. Now we have this integral, a nice little review of a u sub, so I'm going to do that. U is equal to 1 plus 4x. du, or if we have a dx here, du is of course 4 dx because it's just the derivative. So we're going to form a new integral. We're going to write u to the 1/2 because we want to write it as a fraction because we're about to do the power rule. Keeping in mind, of course, that we're trying to change all of our x's to u's. So because we changed 1 plus 4x to u, now all we have to do is isolate dx. Well, what is dx? It's du over 4. If you want, just review our u sub videos from the past. We have so many of them. But dx is equal to du over 4. Just like normal, we're going to write du and we're going to put the 4 outside. 1/4, we're going to drag it to the front so we don't have to worry about it when we take the antiderivative. Remember that you do have to change the numbers, of course. So these were old x numbers. We want to have new u numbers. So what you do is you take your old x numbers and plug it into the function that says u. So when you plug in 0, it looks like you're going to get 1 on the bottom. Then when you plug in 2, looks like you're going to get 9 on top. 2 times 4, 8 plus 1. So remember that once you have this step, you forget about x's for the entire question. All you're thinking about is u's. So let's try to do this. What's the antiderivative? Keep in mind that we're no longer taking derivatives, which is this part of the formula. Now we're taking antiderivatives. So it's going to be u to the 3/2, 2/3 times this 1/4 because that's the power rule. We add 1 to the exponent, 1/2 plus 1 is 3/2, and then you flip the new exponent in the front. Keeping in mind that these 2 and this 4 cancel, so I'm going to do that real quick. And finally, we're going to plug in 9 and 1. So you might not know 9 to the 3/2, but 9 to the 3/2, keep in mind that it's always easier to take the square root and then cube. Sorry, this is not 1/3, it's actually 1/6. Let's try to be a little bit more careful. It's 1/6 again because the 2 and the 4 cancel, it's 1/2. There's still a 3, so it's 1/2 times 1/3. But again, right now we're doing fundamental theorem of calculus. It's going to be 1/6 times 9 to the 3/2 minus 1/6 times 1 to the 3/2. Again, when you do your fractional exponents, just do the denominator first, get a smaller number, and then cube. So in this case, we're going to root first. 3 root, the cube root of 9 is, not the cube root of 9, the square root of 9 is 3. Then we cube it. So again, I'm doing the denominator first, then I'm doing the numerator. So we get 3 cubed, so it's 27. 1 to anything is 1, but you can still do the same thing. The square root of 1 is 1, 1 cubed is 1. Always taking the root first, then doing the power. So it looks like we have 27 minus 1, which is 26, over 6. Looks like our final answer is going to be 26 over 6, which is the same thing as 13 over 3. But you probably won't have to do this process ever because it's a very contrived question so that the integral is actually possible. Still the same formula though, of course. Same number to same number, square root of 1 plus the derivative squared. And that's all it is. Keep in mind that arc length does appear on the last part of a BC area and volume free response question because they provide you with a nice graph, then they ask you to find some area and volumes, and then the last part they might ask you to find the perimeter of the region. So we're going to do that question. So it's a really similar thing because it involves the arc length formula, but with a few added steps at the end. So again, I have this nice beautiful picture. This is going to be a graph of y is equal to e to the 3x. This is going to be the point 0. This is obviously the y-axis. This is going to be the point 1. And then what we're going to do is we're going to, we have this graph. I can't draw this graph. Let me label it over here. And basically what it's going to do is it's going to be cut off at this point. So it forms this region. So notice that this region right here, what we want to do instead of finding the area and the volume by rotating it or something like that, which we did in previous videos, we want to find the perimeter of this region. So we're going to try to find the perimeter of this region over. So let's look at this perimeter. If you were thinking about fences, well, I think that this consists of 4 fences. The first fence will be this line right here, this vertical line right here. Then there's a vertical line on the left side. Then there's a horizontal line on the bottom. And finally, there's this weird function that sort of is the top fence of this region. What is the region R? We probably should have explained it in the first place. It's the region bounded by the x-axis, the y-axis, y is equal to e to the 3x, and also the vertical line x equals 0. The y-axis, the vertical line x equals 1. So again, we have this region, and what we're going to do is we're going to find the perimeter. So we're going to write the perimeter. And what we're going to do is we're going to just add up the 4 fence lengths together. So we're going to find this length, then we're going to find this length, we're going to find this length, and we're going to find this length. And usually when these questions are presented on the AP exam, it will say something like you can just set up an integral, but you never have to evaluate it, because again, these integrals are pretty crazy. So what we're going to do at the beginning is just practice the arc length formula again. What I'm going to do is I'm going to find the length of this guy right here, the top curvy part of this region. So all it is of course the integral from 0 to 1, because those are the x values. Then we're going to put square root, and then we're going to put 1 plus the derivative squared. The derivative, of course, requires the product, the chain rule. So what's the derivative of e to the 3x? Well, that's 3 e to the 3x, 3 e to the 3x. Let's not forget to square it. So if you were to simplify it, you would also square this 3. So it'd be 9 e to the 3x squared. So 9 e to the 6x. So, because when 3x times 2, that's how exponents work. So this is just the length of this top thing right here. Again, I wouldn't sort of simplify this because you can just type in a calculator, but we do need to find these lengths right here. So basically, when you're doing these perimeter questions, just remember that you don't do the formula for vertical lines and horizontal lines, because it's very easy to find the lengths of vertical and horizontal lines. Basically, what's the length of this guy? Well, it's on the x-axis. How long is it going to be? Well, it's going to be from 1 to 0. So what's this side? It's just going to be 1. So it's going to be plus 1. So it looks like this perimeter, we can just write P here for perimeter. This is going to be 1. This is the bottom side. Then we have to add these 2 vertical side lengths. But again, don't employ this formula for this. Only employ the formula for the curvy arcs. So how do you find the vertical side lengths? Well, it's just going to be the y values of this graph. Notice that when you plug in 0, you're going to get e to the 0, which is 1. So how tall is this? It's just going to be 1. So it's going to be 1 plus 1. Then how tall is this one? Well, we're going to plug in 1 into this function. We're going to get e cubed. We're not going to be able to evaluate e cubed because nobody really knows what e cubed is, at least off the top of their head. But again, all I did was plug in 1 to see how tall this is. So it's going to be 1 plus e cubed. Finally, plus this integral, and we are done. So again, a lot easier than our area and volume questions. What we do is we just break up this perimeter of the region into 4 separate parts, just the natural sides of this region. Sometimes it's 3 parts, sometimes it's 4 parts, sometimes it's 2 parts, whatever it is. Then for each length, if the length is not a vertical or horizontal line, you just employ the formula. Even if it's a straight line, you can still employ the formula, or you can do the Pythagorean theorem. But I like to employ the formula. So for example, in e to the 3x, it's going to be square root of 1 plus 3 e to the 3x squared. Then what's the length of these guys right here? Again, it's the y value, and then this bottom side is just going to be the length between 0 and 1, so that's going to be 1. And then you just add them up. Usually you don't even need to simplify it, so you can leave your answer as this if you want. So again, perimeter isn't bad. For non-vertical and horizontal lines, employ the formula. For vertical and horizontal lines, just use the x values and the y values of the region to find how long those things are. And that's it. I'm going to do one last question, which I once saw in an AP exam. It appeared in a multiple choice question, which is approximating arc length with a Riemann sum. And that's all it is. So I'm going to erase this. Just a nice little practice of Riemann sum before we go. A very rare question, but you never know when it might pop up. Let's suppose that we have a function here where we know that we have some x values, we have some f values, and then we have some f prime values. And we're just going to populate this table and with random numbers, 1, 3, 8, and 9. Then we'll do 2, 6, 1, and 4. And then finally, 3, 5, 7, and 2. So this is going to be my table. And what I'm going to try to do is I'm going to try to approximate the arc length, which is the formula we've been practicing, using a Riemann sum. And we'll choose right Riemann sum. And of course, it's of f. This looks like a word off, so we'll write of f using a Riemann sum, using the intervals in the table, so 1 to 3, 3 to 8, 8 to 9. So whenever you have a weird Riemann sum question, what I would suggest is just to remember that Riemann sums are approximation of integrals, so just write what integral you're trying to approximate. So in this case, it's the formula. It's going to be the integral from 1 to 9, the arc length. We can probably say approximate the arc length of f from 1 to 9. So what integral are we trying to do? Well, it's going to be the square root of 1 plus the derivative squared. And we're going to use a Riemann sum. So keep in mind that because the integral involves f prime of x, but not f of x, we're probably not going to use the f of x row. We're going to do the f prime of x row. So let's try to do this. So again, it's always the difference in the x's times the height, where the height is this thing right here. So what we're going to do is a right Riemann sum. So the first rectangle is between 1 and 3, so it's going to be 2 long. That's the base of the rectangle, 3 minus 1. Then you multiply by a different height value. So we're not going to multiply by 6 or 5. What we're going to do is we're going to take this and plug in 5 into this to find the height value. So it looks like it's going to be square root of 1 plus 5 squared. And we'll deal with that later. So let's do the next one. Well, the next one again is going to be 8 minus 3, which is going to be 5. It's always the difference in the x's times different y's. What we're going to do is we're going to use this right value of f prime on this interval. So the f prime value on 8, which is 7, but we're not going to use 7. We're going to plug in 7 into the function we care about, which is not just f prime, but the square root of 1 plus f prime of x. We're going to plug that in. So it's going to be 1 plus 7 squared. And that's going to be the second rectangle. Finally, our third rectangle is going to be 9 minus 8, which is going to be 1. Then it's going to be square root of, again, you plug in the right endpoint into your function. So we're going to plug in 9. So when you plug in 9, it'll be f prime of 9. That's going to be 2. So it's going to be 1 plus 2 squared. If you want, you can simplify this, of course. You might see this in an answer choice. This is going to be 2 square root of 26. 25 plus 1 plus 5 square root of 50. And then finally plus 1 square root of 5. I think 50 you can simplify because it's 5 times 5 times 2. So you can take out a 5. So this becomes 25 root 2. Can't really simplify 26 because it's 2 times 13. So we're going to write this. And then again at the very end, square root of 5. That's a little bit of an arc length question that is very rare S in a Riemann sum, but I wanted just to highlight it because I saw it before. But just keep in mind that it's still the same formula. This is the formula that we talked about a lot today. It was the integral of the square root of 1 plus the derivative squared. When you're finding perimeter, you might be doing vertical and horizontal lines based off the axis, but for everything else, it's the integral of 1 plus the derivative squared. Even if it's parametric, it's integral of the derivative squared plus the derivative squared. And that's all it is. Hopefully this video has been pretty easy because again, arc length is the easiest part of area and volume. Of course, if you want more practice of this, we do have a Girls Teach Calculus video in the link below where one of my former students practices a lot of derivatives because she sets up this formula a bunch of times. On the back side of that worksheet, I believe, that she discusses in the video, she does practice questions involving perimeter of the region. But that concludes our area and volume unit. Go back and watch our area and volume by revolution and volume by cross-section videos if you're having trouble with that, because that's a lot harder, not a lot more harder, but a lot harder than this, because arc length is easy because it's the same formula every single time. We appreciate you, of course, watching our videos. Give us a like and subscribe if this was useful for you at all. But until I see you next time, thanks again for watching.